Hi, everybody, and welcome to this session of Astronomy 120. Today is Tuesday, November 15th. Thank you, Susan. And again, we are in week 14. Next week is Thanksgiving break. So we have quite material. Actually, we have a little bit of material actually left in this class. We are going to deal today with the stars. We're going to build on what we learned basically on the HR diagram. And we're going to see the stars and how they evolve in general, based on our survey of the stars and based on what we know the current models, basically the numerical models for the stellar evolutions. So this is basically the topics for this week. We're going to see that there are 3 possible scenarios for how stars end. Actually, there's a 4th one, but we're not going to mention that. That is for the extremely small stars. So there is the white dwarf scenario, which is for the medium or small stars in general. And then 2 possibilities for the large stars, for the big stars. Either a neutron star if they're not too big, or as being black holes if they're too big. So that's basically the 3 outcomes that end up with when a star basically goes through the entire life cycle and how it dies. So this is basically what we're going to be covering. So let me log in into the, let me share with you the content. And let me find unit 60. So again, unit 60 deals with the phases that the stars go through, basically from a protostar stage to a main sequence star to a red giant stage, and then to its death. And as I was saying, basically, the death depends on, actually, the outcome depends on its size, depends on its mass, I mean. Okay. How long it takes for a star to go through its entire life cycle also depends on its mass. The more massive stars, the shorter they live, the faster they go through their fuel, basically, and they die faster. So this is basically, in a nutshell, how this process works. Okay. Again, stars, they live over a long period of time. So when I say short lifespan for big, massive stars, that's of the order of what? The not too small ones, probably billion years, 10 million years, 100 million years. That's a long time. That's a long time by any stretch of imagination. So based on our survey of this, the night sky, we will see some stars at different stages of their life cycle. For example, if I look at Betelgeuse, I know it's toward the end of its life cycle because of the fact that it's a red giant already. I see some other stars, especially now with the advent of James Webb, that are actually in their early stages. They're even before their ZAM stage, before their 0, basically, age, where they're started. So they're actually still in the protostar stage. And then when we see other stars, they're at different phases of it. So basically, we combine this whole thing, and we can tell, okay, this is how a star would go through its life cycle. And there is an analogy for that that typically is actually textbook analogy, basically, that everybody refers to is, let's say, for example, an alien civilization flies by the planet Earth and takes a picture of all the humans on Earth. Obviously, that picture will involve old people, middle-aged people, people who are in their teens, and people who are just basically born. So this picture, then the person concludes, or at least the alien will conclude, that a human being will go through these stages. They are born first, and they go through a teenage stage, then a middle age, then they age, and then they die. Because ultimately, even the picture will include some of the tombs for people who passed away. So that's how the analogy is. So that's exactly what we're doing now. So we look at the sky, we are short-lived compared to the star. The star lived for a long time, and they take a long time to evolve through their process. So what we do in this case, we take a picture. Even if it takes 10 years for our lifetime to take a picture, it's still a snapshot compared to how a life of a star is. even 1,000 years, and we were not taking pictures for 1,000 years. It's still a very, very short time. It's basically like taking a snapshot of the night sky. Stars evolve, and they take a long time compared to the human basically span. So that's how it works. So you take pictures, you see stars at different ages, and you conclude that. Furthermore, there is a computer models, okay? You simulate a star based on its size, based on its composition, based on basically how much hydrogen it has in its core, and based on the rate of nuclear reactions that it can have. You make a model and you simulate it. Of course, you expedite time. You're not going to wait 10 billion years for the sun to go through the entire cycle. So basically, you make scale better, and you see how a star evolves. So that confirms what we already observed. So there is a correlation between the two. Therefore, what we're saying in here is more or less accurate. So this is basically how we're arriving at these conclusions. So again, when the star is at its main sequence stage, basically, where it spends most of its life, basically, it's just fueling hydrogen in its core. When it does that, that generates temperature. That temperature creates an outward pressure that balances the inward pressure due to the force of gravity, and the star is happy to live most of its life in that stage. However, when it runs out of fuel in its core, namely hydrogen in its core, then in that case, there is a problem. Depending, of course, on its mass, there are different stages that it can go through, but those are very short-lived compared to its main sequence life. And again, there are two possibilities in here. Either it's a small star, low mass star, or it's a high mass star. A low mass star can end up in being a white dwarf, and this is where the sun is headed. Okay. Or if it's a high mass star, then one of two possibilities: either it's going to leave behind a neutron star or a black hole. So that is basically the two possibilities that we are facing at this point. So for a low mass star, you have few light years of interstellar cloud that start to come together due to the force of gravity. Again, this model, we used it to explain the solar system, and it works beautifully for the solar system. And actually, it works also for other stellar systems out there. So that's basically what we believe is correct in this case. So this is a low mass star, so it does not really require a lot of materials to form, okay? And in central location where that gas starts to coalesce, that's where the star starts to form. It's not a star yet until it fuses hydrogen in its core, until it produces energy on its own. Right now, the only energy that is making is due to the converting potential energy due to the force of gravitational potential energy to kinetic energy. And kinetic energy is heat. So it's taking one form of energy and making out of it another one. So at this point, it's still not a star yet. And it shrinks to about, from few light years to about 200 astronomical units. This is a very, very small distance, basically. It's a fraction of its original size. But because the material now is shrunk to that size, that's roughly how big any stellar system is, okay? The sun's extent probably is about, what, 200 astronomical units? That's very far. I mean, just to give you an idea, that's probably the extent with which the the Kuiper belt can go. No, actually, the Kuiper belt can go only about 50 astronomical units. So this is basically a big region for the star. Okay, and at that point, there's two bipolar outflows. They come because of the conservation of angular momentum, really. So it's still not a star yet. But then, at some point, nuclear fusion starts to happen, and at that point, it triggers, and it's going to clear most of its gas in there, except the heavy objects that are left behind, like planets, like for the case of the Earth, or even smaller than that, like, for example, moons, or even dwarf planets and stuff that is far away. It can still be basically remain intact to some extent. So at that point, it has entered its main sequence stage. This is typically the size of the sun. This is how it's going to go. At this point, it's a yellow star. Looks white, actually. Okay. Once it runs out of its fuel, this is where it spends most of its life, in this stage. At that point, it runs out of its fuel in the core, so it's going to start burning the hydrogen in the shell above, or the helium that was formed. Now, the reason why this is so, because now it's going to shrink because there is no more fuel to fuel it. So gravity starts to win. And as it shrinks, now again, you're converting potential energy to kinetic energy, it's getting hotter to a point where helium actually starts to fuse. Now the outer shell expands. And as it expands, it cools. So its temperature goes from white to red. And it expands now, it's a red giant. At some point, it's going to shrink again because of the fact that it's going to run out of fuel inside either. So it's going to, the force of gravity starts to win again until it gets hot enough. So it's going to be a yellow giant. And then it's going to fuel more of the higher elements. And it's going to go through a second red giant stage, which is even bigger. That's going to be a short-lived period, after which it's going to basically run out of fuel completely. There is nothing in it that's going to help it basically keep its keep it from falling further. So it's going to fall further. And then the reaction to that is that gas that is going to form, that is going to escape, and that is the planetary nebula. The planetary nebula will feed new stellar formations. So imagine that this is what happened to the sun. It's about 1 light year, of course. But if there are enough of them in here, you will have few light years in here that they start to coalesce again and form a new star if need be. Or they can, if it's isolated, it's going to be part of the interstellar medium that has a lot of materials in it that is left in there. But what is the outcome in here is the core itself of the sun will be a white dwarf. This is about the size of the Earth. So a white dwarf, basically, imagine the sun right now, which is about, you can take 1 million Earths and fit them in it, down to basically the size of the sun. However, in terms of mass, it's still big. So this is a super, super dense material in here. It's extremely dense material. Density is extremely, ridiculously high. So at this point, if it's not part of a binary, this is the end of it. This is the end of the star. But if it's a part of a binary, there is a little bit of complications that happen because of its neighbor, then there is a potential for interaction between the two. In other words, it could feed off of its neighbor and then basically have a new lease on life, basically, again, because of the fact that it will grow more materials in it and start fusing and start doing all kinds of weird things again. Or it can go even to supernova. So this is for a low mass star. For a high mass star, the scenario is similar, except instead of few light years, you have several light years, more materials to start with. And it's going to go through a protostar, and it's going to go quickly through the protostar to start basically its life as a star. And the density in here, because it does not really have enough time to start forming immediately like this one starts slowly. This one is faster because you have more materials. It gets together. Now there is more chance for hydrogen and hydrogen to collide, and now to basically fuse. And now you have a main sequence stage. Even through the main sequence stage is going to be faster because of the fact that you're fusing. You have a lot of hydrogen to begin with, and it's a nearby, so the probability for it is higher to fuse. Furthermore, there is another process for it to help it basically with the nuclear fusion. It's not the proton-proton chain, it's the CNO cycle that's going to help it basically faster, go through its fuel faster. That's why it's going to live very short life compared to a low mass star. It's going to go through a pulsating stage in here as a yellow giant, then a red supergiant, and then an explosion. And like the nebula that forms for the case of the planetary nebula in here, this one is actually a very violent event. It's one of the most violent events that you can ever witness. Now, the gas that is ejected is going to be part again of the interstellar gas. And if there is enough of it, again, it's going to go and feed the new stellar formations. This is what we think actually happened to the sun. The sun must have formed through this leftover of this materials and other materials, because of the fact that we know the sun has higher metallicity, namely has heavier elements in it. Case in point, the Earth has iron in it, has nickel in it. Those, they don't form from a low mass star process. This low mass star process will not produce those heavy elements like gold and all of the other materials. So they must have formed, they must have been left over of the previous supernovae that happened in the area where we were, at least one of them, if not more. So that is basically how the sun was formed. It was formed of some leftover of the materials like this one. And that's why we are here now to talk about it. I mean, we have iron all everywhere. That's a signature of a big star that has formed. Iron cannot be formed with low mass stars. So again, depending on the size that you started with, the core that has basically collapsed on itself can collapse and basically is to a point where neutrons are neutrons. There is no problem with that. But the protons and the electrons, they are forced very close from one another until they fuse. So you have a proton and an electron, they fuse and they become a neutron. So you have already starting with enough neutrons to begin with. That's a common element everywhere. But now the protons that existed are converting to neutrons. Hence, it's either predominantly neutron or actually all of it neutron. That's what a neutron star is. But this process can be overcome for far more massive stars to a point where even this is overcome, to the point where the whole thing collapsed inward in itself and forms a black hole. So it's a singularity. So this can only happen for supermassive stars. For the case of the white dwarf, for example, this is not possible because you don't have enough materials. So protons stay proton, neutrons stay neutron, and there is basically, yes, you can have a plasma state where the electrons are floating by themselves or floating basically separate from their nuclei. But at the end, is still definite material in here that is not merely neutrons. And like this scenario in here, where neutrons are actually the leftover from that. Neutron stars, they come in different flavors also, either a regular neutron star, which is an old one, or the newly formed neutron star, which is either a pulsating neutron star, which is a pulsar, or actually having a supermassive strong magnetic field called the magnetars. We're going to get into the distinctions later on for the neutron stars, and they are beasts on their own. They are actually the worst thing that you can encounter, other than the black hole, of course. Those are actually worse than that. So this is basically one of the two scenarios that that are going to happen for the end of a big high mass star. The thing to remember with the distinction also in terms of their life, okay? Yes, Joseph, sorry. Even the white dwarf, you don't want to be near it too, because there can be also beasts on their own too. So they're all actually different kinds of animals. Anyway, so the point being in here is that we're going to cover actually more of these things down the road. I'm hoping, yes, we still have, after this week, we still have at least 2 more weeks of instruction, and then we're going to finish all of these materials. This week we have about 6 units, so it should be fine. So again, this is basically a summary of all of the things I was talking about it in here. And I mentioned the fact that if it's part of a binary, the process can be complicated. Whether it was a binary with one big star and one small star, or I mean, low mass star or a high mass star, you will have a neutron with a neighbor. And then at the end, that neutron starts to feed off of its neighbor and then can go into a supernova. And this is one type of supernova, or actually a black hole that is going to feed off of the other one, and the accretion disk will have all kinds of materials falling into it, and that's going to also have a different stuff. And even with white dwarfs also. And there are new kinds of white dwarfs that are actually been detected recently that can actually have all kinds of complicated interactions with their neighbors. The whole description that we have discussed up to this point is that for a star that is by itself, which represents about half the stars out there. So again, these are the three outcomes. A white dwarf is about the size of the Earth in terms of physical size. So it's a big star. And but if you, for example, one of the famous ones is actually Series B. Series stars are which is the brightest star in the night sky. Actually, of course, it's the just basically in terms of stars, it's the brightest one, other than the sun, of course, which is a very close star. But the point being in here is Ceres actually is two stars, the A and the B. The B is actually a white dwarf, so this is actually a very close one, and this is of the size of the Earth. Okay, and now there are pictures of it, so we can take pictures. But a neutron star is actually something that is actually of the size of a city. It's only a few kilometers basically wide, so it's really not that big in terms of physical size. A black hole is a problem. How can we define the size of the black hole? There is something, and we're going to talk about that one later on. There is the event horizon, the disk, the radius with which after that light, even light itself cannot escape. A single roaming basically black hole by itself cannot be seen unless it goes between it and another star, where you can see it pass in front of it, and even then it might be confused with a planet. It's only distinguished from a planet if you observe something called gravitational lensing. The light coming from the star behind it will bend a lot, although it's of the small size. Then you can determine that this is a supermassive object, but it's very small, okay, and it cannot be seen. So this is basically how black holes are. They are actually at least the ones that result from the collapse of big stars. They are very small. However, and this is a big however, there is another classifications of black holes that we, until now at least, we don't really have a full grasp of how they form, and those are the supermassive black holes that have been observed in the center of the galaxies, like our own. In our own galaxy, there is in the center of it, which is Sagittarius A star, a supermassive black hole that is too big to be explained by this process. Okay, how it was formed? It may have formed actually from basically the collision of several black holes together, combining into this one, which is about 4 million suns put together. So it's a big one. So at least the ones that I'm talking about in here, they're small. The ones that formed from the collapse of massive stars are extremely small. There is another type of black holes that is not covered by this discussion. The discussion is coming later on when we talk about black holes themselves. Again, this is how stars evolve on the main diagram, on the HR diagram. Okay, the main sequence line for the stars is again the diagonal that turns from the top left to the bottom right. That is the main sequence stars. Remember the classifications that we had from the previous units? That is basically the main sequence stars. A protostar will evolve from being super cool, its temperature very low, until it reaches a point where hydrogen starts to fuse from it, and the size also changes with it. When it becomes denser, more materials. So initially, more materials get in, it gets bigger and bigger and bigger and bigger. But because of the force of gravity, it's going to pull it closer and closer and closer. So its size starts to shrink. As it shrinks, the temperature goes hotter and hotter. See, that's what you see with the temperature in here. Because if you take, for example, one pillow and put it on the top of another pillow, it's going to form like this. But if you put a third pillow or fourth pillow, they're going to shrink. They're going to push it inward more and more. So the density increases. That's why you see a smaller size for it. And with the smaller size, there is an increase in temperature. Again, you're converting potential energy to kinetic energy, which is heat. But then there is enough heat, temperature exceeding about 10 million Kelvin. At that point, nuclear fusion starts, and the star now becomes a star. I mean, the protostar becomes a star now. It's going to spend most of its life in here. While doing so, it's going to basically expand. And as it expands, its temperature increases. That's why you say it's shifting in this side, in here. Then what happened to the sun? Actually, until it reaches a point, but not that much really, until it reaches a point when it runs out of fuel, then it's going to go through the red giant stage, then it's going to shrink in size again and go through the yellow giant stage, and then it's going to go through the second red giant stage, and after that it's going to form a planetary nebula that is going to be ejected from it, and the core will start to basically, yes, it's going to heat initially to a tremendous temperature because of the collapse, because remember we're converting potential into kinetic, so it's going to be very hot, and then it's going to start to cool down. As it starts to cool down, its color starts to shift. Initially you cannot even see it, but then it's going to start to shift until it becomes a white dwarf. And it's going to take billions and billions and billions of years to lose that heat completely and convert from a white dwarf to a black dwarf. Now, for the big stars, the high mass stars, those they start in a similar fashion, except you have more materials to begin with. Remember, you didn't start with a few light years, you started with more light years, okay? So you have more materials to gather, and it's going to go rapidly through its stage, and in doing so, it's going to immediately start fusing. It's going to spend a little bit of its time in here, and then it's going to go through a super red giant stage, and after that, it's going to explode into a supernova, leaving behind one of two possibilities, either a neutron star or a black hole. There is a very, very important point, and the reason why I'm saying that, because I was asked this point at least 2 times in the past, way in the past. Now at least I make more sure that you guys understand it. The star, physically, it's in the same place. It's just the shape changes, that's all. The shape and the temperature and the color and all of that change, that's all. But it's not moving in space. It's not actually traveling along any curve in here. This curve represents its temperature versus its luminosity and its size. That's all. So this curve is not a migration of the star moving around and getting somewhere and then, no. I actually kind of, let me correct myself quickly in here, and I always do that because sometimes it's kind of confusing a little bit. Stars move. And they move because of the interactions with the remainders of the stars and the galaxy. Like the sun, for example, goes around the galaxy. It takes about 250 million years to go once around the galaxy. The star is about what, 5 billion years? 5 billion years divided by 250 is what, 4 times 5. It's about 20 times it went through the site. Through the entire 5 billion years, it went roughly about 20 times around the galaxy because it takes so long to move. And all stars do. All stars do move. However, this motion is not real. I mean, what looks like it's a motion in here, it's not that motion. This is actually, whatever it's supposed to be, it is, but its color and size change. And its temperature change. That's all. Okay, I hope this point is clear in here. Sounds good, guys? Okay, so very good, thank you. Let me share with you the other unit now. As you guys see, I mean, we've been doing this from the get-go, and we're not covering all of the units, so I'm really relying on you to read the units that we're not covering, these for your own personal, basically, education. And also, even the units that we're covering, this is what we're doing in here is not in lieu of that reading. So you still are required to go through those units on your own, okay? Just want to make sure that you guys understand that. Okay, again, we're going through a new cycle now we didn't discover before. We talked about before in the proton-proton chain. Remember, in proton-proton chain, you have 6 protons. Remember, inside the core, there is hydrogen that is ionized, meaning you have protons with electrons that are floating by themselves. The protons, they come together, 6 of them come together, producing one alpha particle, which is the nucleus of a helium. So you have a helium that forms. In addition to that, two protons are actually put back into the pool of protons to interact with things. So you have 6 come in, 2 come out. So technically only 4 are needed, but you require it for 6. And then one helium nucleus is formed. Plus, a lot of gamma energies, a lot of photons in the form of gamma, and gamma we cannot see. So how in the world we can see the sun or the stars to begin with? Well, in this case, the gamma rays, they hit the electrons mainly inside the core, and in doing so, they impart part of their energy to the electrons and lose some of that energy. When they do lose energy, their frequency drops. When the frequency drops, the wavelength increases to a point before they leave the core. At that point, they become more in the visible range that we see, in which case they travel through the radiation zone, then the convection zone, and they come to us. It takes about 100,000 years for them to leave the sun, from the time they form to the point where they reach us. So that is a byproduct. So the product of 6 protons coming together, forming a helium nucleus, plus 2 protons that are going to be put back into the mix so that they can do whatever they need to do also with the other protons, so that they can start another process somewhere else. And energy, which is in the form of light, plus 2 neutrinos. And that is the only particles that come straight shooting from the sun to us, telling us what's going on inside the sun. So this is, in a nutshell, the proton-proton process for the sun. It's a low mass star, so it has enough temperature for it to do this process, but not high enough temperature to do something else. And the rate with which this process takes is extremely slow. In other words, if I were to track those protons inside the core of the sun, it's a very, very unlikely possibility that any of them will do this. Most of them, they go their happy life completely unaware of this process. So this nuclear reaction, the proton-proton chain that is responsible for the sun's activity, is extremely rare. But because the sun is supermassive and a lot of it, a lot of hydrogen inside the core, there is enough energy that comes to us that shines every day. And the sun will live for about 10 billion years. There is another process, though, and the process that I was talking about is a CNO. It's a much faster process, and it's going to have the same outcome. It's going to result in the same possibility with almost the same amount of energy also. The only difference is this is a much faster process, and this is for higher enough materials, for a high enough high mass stars. You have a chance for doing it, and that's exactly what's going on in the high mass stars. Actually, there are 2 processes. One, which is a very rare process. So the proton-proton chain in the high mass stars is a really negligible process compared to the CNO process. So again, you need that reaction inside the core to maintain the star from collapsing. Otherwise, gravity will force it to collapse. So you need reactions inside its core, whether being a proton-proton chain or a CNO cycle, to basically make it so that the star does not collapse. So when the star is forming, so this is again another reminder that's all about what we're talking about. So when you have less mass coming together to form a low mass star, in this case you have a weaker force of gravity because you have less material to begin with. Okay, so it's going to take more time, and as it does, it's going to compress the star further. And once it does, the temperature will reach a certain temperature, and now the nuclear reaction starts in it. So it's a little bit denser than in the case of the high mass protostars that are starting to form and make the new stars, because you have more materials, and before you reach that peak density, if you wish, of the materials, you have a lot of hydrogen already there, and the nuclear reaction starts. So high mass stars, they have less dense core than that of a low mass stars, because they start the nuclear reaction too soon. compared to low mass star. So this is a distinction between the two. As I was saying, the main process really for a high mass star is the CNO cycle. But for a big star, for a low mass star, they rely on the proton-proton cycle, proton-proton chain, actually. Okay, because it's not really a cycle for the proton. And then it starts with 6 protons, you end up with 2 protons plus helium plus neutrinos, 2 of them, plus energy. This one, on the other hand, it's a cycle. When I say it's a cycle, it's a circle. When I say a circle, you can start anywhere you want to. Anywhere you want to, you're going to come back to the full circle. Typically, I like to start from a regular carbon. This is carbon 12, okay? That's most of the carbon that you will find in nature. I mean, there is carbon 14 in nature, but carbon 14 in nature is rare compared to carbon 12, okay? So you have carbon that has what's formed in the core of the sun. Remember, it's less density than the core of the star, less density than the sun or the low mass star. So it must have formed it even through using the proton-proton chain. So you have carbon in here, captures one of the protons. Remember, this is a high temperature, even higher temperature than that of the low mass stars. Captures a proton and produces a gamma ray. These rays, again, they're extremely high energy. So they are not going to leave the core of the star immediately. They're going to take a long time after bouncing with mainly electrons before they come out in their whatever color that they need to come out. Okay, typically they come out in a higher energy than the ones for the low mass star. Now you have a proton added to a carbon. Carbon has 12 protons. You add a proton to them, and the chemical chemistry changes from carbon to nitrogen. Nitrogen on the periodic table is actually the next element after carbon. You look at the periodic table, carbon is here, and nitrogen is here. Carbon normally has 6 protons. I'm sorry, did I say 12? 12 nucleons. Namely 12 combination of protons and neutrons. It has 6 protons and 6 neutrons. Okay. Nitrogen has 7 protons. So where does the 7th came from? It came from the one that it captured. But normal carbon has actually 14. If you look at that mass, if you can see this or not, I have the periodic table in here. Okay, I'm looking at these 2 elements in here. I know some of you are in my lab, so we should be able to see this in the lab also. So nitrogen has 14. Most of the nitrogen that you see in nature has 14 protons. I mean, 14 nucleons, which is a combination of protons and neutrons. But this carbon is not 14. This carbon is, I mean, this nitrogen is not 14. It's actually 13. It's short 1 neutron to become a regular nitrogen. So this nitrogen is an isotope of the normal nitrogen. So it's not really stable. It's metastable. So what happened in it? It's going to automatically convert any of the protons, whether the one you just added or any of the existing protons, to convert it back into a neutron. And we'll be left only with 6 protons. And 6 protons is exactly carbon again. So we're back to carbon in here. In doing so, it's going to emit a positron, which is a positive electron. It's going to immediately meet an electron. Remember, we're inside a sea of electrons. So there is electrons abound everywhere. So the minute the positron is formed, it's going to encounter an electron, and immediately they will cancel each other. They will annihilate one another and produce more gamma rays, more energy, more light. But then there's a neutrino. So now we keep tab of what has come out. The positron is going to be energy, just like this energy. So we have energy coming out, plus a neutrino. So we have 1 neutrino out. This carbon 13 is just like carbon 12, the normal carbon, except that it has, instead of having 12 nucleons, namely 6 protons and 6 neutrons, it has actually 6 protons and 7 neutrons. This is not a stable 2. because carbon on its own most of the time is 12. That is the stable element in the periodic table. So what happened in this case actually is going to capture proton. When it captures proton again, it's going to move on the periodic table from being carbon back to nitrogen again, because now it has one more proton. So and this is the stable, this is the normal nitrogen. This is the one that you see in the periodic table. That is the normal nitrogen. That has 14 nucleons, namely 7 protons and 7 neutrons. But you have a bunch of protons that are floating at extreme high speeds. Another proton will be captured, and now you move to oxygen. You move to the next element in the periodic table, because now instead of having 7 protons, you have 7 plus 1, which is 8 protons. And 8 protons, according to the periodic table, is the oxygen. The next element in the periodic table is oxygen. Now you have oxygen, but this oxygen is a weird oxygen. This is oxygen 15. Oxygen 15, which is here, most of the oxygen in nature is 16. You have 8 protons and 8 neutrons, 16 nucleons, whereas this one has 8 protons, like it should, but only has 7 neutrons. This is not stable too. So what happened in this case? One of the protons, it doesn't matter which, automatically changes due to radioactivity to a neutron again. So instead of 6 plus 7 equals to, instead of 8 plus 7 equals to 15, it's going to be 7 plus 8 now equals to 15. But now instead of 8 neutrons, you have actually, instead of 8 protons, now you actually have 7 protons, back to nitrogen again. But this nitrogen is again 15. But the outcome, 2 things come out. A positron, which is a positive electron, will immediately meet its counterpart, namely a regular electron, and they will annihilate, producing more energy. And there is a second neutrino. Neutrino here and neutrino here. 2 neutrinos come out of this process. This nitrogen 15 is not stable. It's going to capture a proton. And now you have, remember, we have 7 protons plus 1 proton, that is 8 protons, plus another 8 neutrons that existed, for a total 12, for a total of 16 everything, protons and neutrons. 4 of them are freed from the 16. 2 protons and 2 neutrons, which is regular helium, come out of the process. And now we're back to carbon, and the process continues in the whole cycle again. So let's tally what happened. Let's sum up everything. First of all, the things that really came into, so these things, they don't change. Carbon, nitrogen, oxygen, nitrogen, carbon, nitrogen, so it's a circle. So these things, they're what is known as a catalyst. Catalysts are facilitators, that's all. So the actual process involves 1 proton, 2 protons, 3 protons, 4 protons come in to this cycle. The outcome is energy from the annihilation of this positron, energy here, energy from this annihilation of this proton, and that's it. Add up all of the energies if you wish. That is a byproduct of this reaction. And that's the whole purpose of it. Because the star wants to stay intact, doesn't want to collapse, so it needs to produce heat. And that is really the whole purpose of this whole thing, is the energy. It doesn't want to produce helium. That's not its purpose. It's not in the business of making neutrinos. That's not what it wants. It wants to make enough energy to prevent it from collapsing. That's all, because gravity wants to collapse it, so it wants to make enough heat. So that is the energy. The energy produced by this cycle is similar to the energy produced by the proton-proton chain. Now, that's not the only thing that is made up through the process. There is this neutrino, and that is this neutrino. 2 neutrinos, similar to the proton-proton chain that produces also 2 neutrinos, by the way. Also, an alpha particle, namely the nucleus of helium, is also produces similar to the proton-proton chain. So in this case, it's really a real cycle that involves carbon, nitrogen, oxygen. Those are the words that are in the CNO cycle. And that is basically how the process is. You can take it anywhere you like. It doesn't matter where you take it. I like to take it from the carbon, but you can take it anywhere because it's a complete cycle. And like the proton-proton, which is sometimes referred to as a proton-proton cycle, it's not really a cycle, it's a chain. Starts from where, ends somewhere else. You need another process to start independently for that one. You can't expect it to loop around itself, okay? So this is the difference between the two. The energy produced is almost the same thing between the two processes. So the star will, but the biggest difference also is the fact that this process is much, much faster. And the distinction is coming from this process involving the formation of neutrinos. If you would want to convert this oxygen 15 to nitrogen 15, or this nitrogen 13 to carbon 13, in this high mass process, it's very fast. It doesn't take too long compared to the other process. If you guys remember, when the proton-proton come together and they form basically what looks like two protons, one of them changes to a neutron. That process takes a long time, actually, to even for the possibility for them to fuse. So that process is very slow. This one is very fast. So high mass stars go through their fuel much, much faster. They have more stuff to begin with to fuel, but the process involved is much faster process than the other one. So hopefully you guys have an understanding of how these things work now. Is it clear the comparison between the two? Yes, maybe. Okay. I'm glad that you said that. Then I'm going to rely on you guys to go back through it and go through and read through that. Because when we went through the proton-proton chain at that time, we didn't have really honestly a reference. So it was kind of floating by itself. Now we have a comparison between the two. We have actually a reference. We have a CNO cycle that we can compare to a proton-proton chain to try to understand how stars make their energy. Does this answer your question a little bit, Susan? Yeah. Okay, very good. Thank you. So I hope that you guys go through the reading and go through this, try to understand. In terms of the materials, they're identical. Even the other one actually had, at the end of the day, only 4 protons, making 1 helium and producing 2 neutrinos plus energy. This is the same thing. 4 protons coming together, producing 2 neutrinos and energy plus helium, basically a nucleus, which is called the alpha particle. This is what we call alpha particle. It's the nucleus of helium. That is because historically, radioactivity was studied heavily, and they discovered that there is a kind of radioactivity called alpha, as distinct from beta, as distinct from gamma. And at that time, even gamma was not known to be a radiation. So when we measure the charge of the alpha, it turns out to be twice that of the charge of the electron, and it's positive. And that is because you have 2 electrons that are stripped from the helium. And then for the beta, it was a negative E. For gamma, its charge is equal to 0. So that's why they classified them alpha, beta, gamma for radioactivity. And radioactivity was a very, very fast-moving science at that time. And then when we measured the mass of this one, this turned out to be exactly 4 times the mass of hydrogen. This one turned out to be the mass of the electron. This one has a mass that is 0. It took a little bit of time to realize that this is actually part of the spectrum, the electromagnetic spectrum, part of light, extreme high frequency light. This one actually is a regular electron, beta radiation, and this one later on, which is really the polonium, which is part of the, which is on the periodic table somewhere in here, that was discovered, studied heavily by, what's her name, Marie Curie and all of those people. It's this element on the periodic table, polonium, that produces was called after her country of birth. She was born in Poland. Marie Curie, and I know she grew up later on, or at least she went to school in France and married, what's his name? Pierre, okay? That's how she got her last name, Curie. Anyway, the point being in here is, this is how the alpha, so this is actually an alpha particle. Sometimes they refer to it as alpha particle. And this is a helium nucleus, right? Okay? Again, in terms of internal structures for a low mass star, an average star like the sun, and a high mass star. In terms of convection zones, for a low mass star, because of the slow process, the convection zone really dominates. Most of the star is actually a convection zone. So there is no radiation zone whatsoever. And this is actually very good for a low mass star because it helps mix the gases inside, which is very helpful because it's going to renew more its core to make it active for a lot longer. First of all, the nuclear reactions are extremely slow. And furthermore, it's going to fuse more hydrogen at the long term because of the fact that it's getting more hydrogen from the remainder of the star inside its core to fuse it. So low mass stars, they can live forever, basically. They can outlive anything. This is an average star. An average star, the convection zone is very high because there is a region in here where there is actually a radiation zone that transports some of the heat to it. And because there is a region in here for it where there is not enough radiation, so it's going to be left with a convection. So the difference between this one and this is that the core of the star is really all where the action is happening. And it's not going to go above to the above layers to fuse the hydrogen in those layers. So that hydrogen is out of reach, really. So that's it. Whatever it has in the core, that's all there is to it. For a high mass star, it has a convection zone because it's mixing a lot of the gas in here immediately. It doesn't have, most of it is radiation at the end. That too has more gas in it and is going to get more gas and is going to go through it so rapidly that it's unbelievable. So this is actually the distinction between the stars. Again, I mentioned the zero-age main sequence stars. That's where it spends 90% of its life, okay? And I mentioned earlier that as the star ages through its main sequence star age, it's going to actually grow in size. It's going to grow in size. And the age in here ranges from 10 billion years for the case of an average star like the sun, to about 1 billion years for stars that are slightly bigger, to about only a few hundred million years, to only about 10 million years. That is basically the age. For the ones that are of extremely low masses, they can range for much, much higher than that. Probably 100 billion years, outliving anything in the universe. So by the end of the process, when the sun became a white dwarf, Proxima Centauri will stay there. Proxima Centauri is not going anywhere because Proxima Centauri is a red dwarf. Okay, this is actually a useful formula. I know we're not going to have another homework at least related to this one, but this is a useful formula on how to measure the life of a star. You take its mass, you divide it by its luminosity. The mass as compared to the sun's mass. So it's not the actual mass, how much kilograms there is, how many suns they are. And also the luminosity, not how many watts that it's going to generate, but how much luminous it is compared to the sun. And you multiply that by 10 billion years, that's what 10 to the power 10 is. And that's going to give you the life of the star. Okay, so this is actually a useful formula. Remember, the luminosity also is proportional to the mass, or actually equal to the mass to the power 3.5, or 7/2. In other words, it's the square root of the mass to the power 7. So the more massive stars, because if you do the fraction correctly, this is going to be 1 over mass to the power 2.5 times 10 to the power 5, 10 to the power 10, I'm sorry, years. So the point being in here is the more massive stars, they live less than the less massive stars. That is basically in a nutshell what this whole thing is. Okay. I hope that you guys go through the reading and do at least the examples that are in the book in there so that you understand, because I truly believe that doing numbers really help you understand better the topic. We can talk all day today and you can read as much as you want to read, but if you don't really pull your basically sleeves and do things, you're not going to have this thing remembered or retained. Okay. So let me share with you the last topic of the day. I know we still have time, Okay, so this is actually going to be not that long. We're going to describe the structural changes and what's going on in the stars in general as they evolve. Again, we discussed this extensively, namely the balance between the pressure due to the temperature and also between the gravity. And we actually had this diagram early on today, actually, with between the white dwarf and the neutron or black hole star as they evolve. Okay. So again, in order to go through a red giant, at that point, the core shrinks. This is actually a main sequence. At this point, it's just using hydrogen in its core. But then when it runs out of that, then when it's going to shrink, and when it does, it gets hotter. And when it gets hotter, the hydrogen inside the shell and the shell outside of the core starts to fuse, pushing the components of the star, the rest of the layers upward. So in this case, the star grows in size, and as it grows, there is more heat dissipated through a bigger area now, so the temperature overall outside becomes less and less. Okay. So this is the red giant stage. Again, depending on which one you're talking about, they all are going to end up with much bigger radii. Remember, this is also the radius of the star, and also with a cooler surface temperature. So the surface temperature is a lot cooler because of the fact that you have the entire size now is where the energy is. Okay. Now we are going to have a much hotter temperature inside the core that can start fusing actually helium. Remember, around 10 million Kelvin, 15 million Kelvin for the case of the sun, you have hot enough temperature so that hydrogen fuses, but those temperatures are not enough. In other words, the helium is not moving fast enough to get from each other. Remember, the hotter temperature, the faster the particles are moving. But 10 million Kelvin is high enough for these low masses to approach one another, but this high masses, more charges. That's the main thing. You have twice the electronic charge of a proton, because you have two protons, and you have two protons, so the repulsion due to the force of the electrostatic force is very high. So remember, the repulsion is proportional to the charge, 1 times charge 2 divided by the distance squared times the constant in here, just a constant, forget about that. So you have 2e because you have two protons. E is that's 1.6 times 10 to the negative 12, the charge of the electron, because the charge of the electron and that of the proton is the same. So you have 4 times e squared divided by the distance squared. You don't have enough kinetic energy to overcome this force. But when the temperature increases so high, then you will have enough energy to fuse these two and form beryllium, which is later on can capture another helium and then basically become carbon. So now what you're doing actually, you're fusing helium. You're not fusing hydrogen anymore at this high temperatures. So helium now is part of the process where it's going to fuse. The temperature has increased enough so that the helium starts to fuse itself, forming, among other things, carbon, because potentially even you can form oxygen using other combinations in here, okay? Because carbon is 6 protons plus 6 neutrons. 6 protons, think of them this way. they're coming from each helium is bringing 2 protons, and each helium is bringing 2 neutrons. So you have 3, 1, 2, 3 heliums at the end of the day, combining to form carbon. You could even form oxygen. Oxygen, remember, is 16, meaning you could have 4 alpha particles. Each and every one of them is bringing 2 protons, and 4, the same 4 actually bringing each and every one of them 2 neutrons to form 8 protons and 8 neutrons, and that is oxygen. So potentially, if the temperature is high enough, actually you could even form oxygen, okay? And this is for a little bit bigger, low mass stars. Now, the degeneracy actually is another concept that you have to think about it. If you take loosely compound, basically balls, it doesn't matter which they are, the tennis balls or anything like that, and you start squeezing them, at that point, they're not going to, there is a certain size that you cannot exceed. This is similar to what happened actually in case of the atoms. So if you take, for example, neutral atoms, okay? If you take, it doesn't matter, let's take iron, for example. Iron on the periodic table, it has 28 electrons, okay? And another iron has 28 electrons. The minute you push them next to one another, 2 electrons cannot exist in the same state. This is called Pauli principle. Now, 2 electrons cannot coexist in the same plate and they will repel. So this is really the essence of this degeneracy. So you cannot have this coexistence in here. So at some point you're going to repel. And that is really the reason why white dwarfs really cannot collapse any further. It's because of this electron degeneracy also, okay? 2 electrons cannot coexist in the same place. I think we need to expedite this a little bit. So again, at some point, the temperature is high enough where the helium starts to fuse, and it's going to take a little bit, because now the degeneracy is high enough and the compression is high enough, the temperature increases enough for the helium to fuse, in which case it's going to relax a little bit, okay? Because as it expands, it's going to cool down again. And that is what we call a new lease on life, actually, in this case, because it's going to go back into this stage, and then it's going to grow back into its final stage. Okay. Again, we still have 3 more units this week. We're going to discuss them. I'm going to actually pre-record them and post them for you guys for the session, the second session of this week. Some of you are supposed to be on, we have a lab this coming Thursday, and some of you actually, I think only one of you guys is in the other section. So we have a lab today for that. And I will see you guys live after Thanksgiving on the 29th of November. Meanwhile, you have a quiz and you have other assignments. Please take care of them, including the discussion sessions. Sounds good? Thank you very much, Suzanne. Thank you, Samantha. And happy Thanksgiving to every one of you guys. But don't forget, we still have more materials in this week too. Thank you. I'm going to stop the recording, and I will see you guys later. Thank you.